The graph of f prime is below. Use it to determine where the inflection points are and where f is concave up and concave down. If there are multiple inflection points, separate them with a comma. Okay, so carefully read this problem because we are told that this is the graph of the derivative of a function. It's not just a function, because if it were, we would say the inflection point's probably about right there. But since this is the derivative of some function, we can't use that as the location of the inflection point. What we probably need to do is really start brainstorming and thinking about what the definitions tell us for individual functions. So, for instance, if the original function is increasing, then that tells me that its derivative is greater than 0 on that interval. If the original function is decreasing, then that tells me the original function is less than 0. And if the original function has a critical value, which I'm just going to say a min or max, just for simplicity, that means that the first derivative is equal to 0 there. Now, here's the thing. If I had told you that this was an original function and not a derivative, it changes what the properties of how we interpret individual values, but it doesn't really change the function at all. It would still be the same function. It's just, is this a derivative of some other function, or is this the function itself? The same properties go from a derivative to the original function as a second derivative to the first derivative. So, for instance, here's what I'm saying. If the first derivative has a minimum or a maximum, what that would mean is that the second derivative would have a 0. So, we can use that because if the second derivative has a 0, that is an inflection point. So in fact, what we're looking for here are locations where this derivative has a minimum or a maximum. So right there and right there. Those are going to be the locations of minimums or maximums. So the inflection points are at -2 and -1. Now, where is this concave up or concave down? So when it comes to determining things like that, let's again just think about what it means for the relationship between the original function and the first derivative as compared to the derivative and the second derivative. So if the original function is increasing, then that means its first derivative is less than 0. That's a fact that we know from the very beginning of studying applications of derivatives. But that also implies that if we move down to the first derivative, then that tells me that if the first derivative is increasing, then the second derivative is greater than 0. Or if the first derivative is decreasing, then the second derivative is less than 0. And what's important about that is if the second derivative is less than 0, or greater than 0, that tells me I'm on an interval that is concave up. And if the second derivative is less than 0, it tells me I'm on an interval that is concave down. So, taking a look at that, whenever the first derivative is increasing, so for instance this interval here and this interval here, I am concave up. So this function is concave up on the interval from -∞ to -2, and then from -1 to +∞. And that leaves for it to be concave down on this interval here to here. So from -2 to -1.